Okay, so combinatorial arguments. We've seen Pascal's formula before. N choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Right? These are the binomial coefficients. And note that we can prove this using algebra. Right? N choose k is simply n factorial over k factorial times n minus k factorial. And on the right side, we have n minus 1 factorial over k factorial n minus 1 minus k factorial plus n minus 1 factorial n minus k factorial k minus 1 factorial. So to prove this using algebra, one just has to, well, manipulate the right-hand side and show that you get the left side as a result. So how would we manipulate the right-hand side here? Well, we could write them as two fractions with the same denominator and combine them. So their LCD is k factorial times n minus k factorial. Right, so I'm going to write that as the new denominators for each of them. Right, and so on top here, I'm going to have n minus 1 factorial. Right, that's the old term, and you multiply by n minus k. And on top, on the fraction on the right, I've multiplied by k, so it's n minus 1 factorial times k. So I can combine these two into one fraction, and note that my denominator already matches the denominator of the left-hand side. So I just need to write the top to match simply n factorial, and that's easy to do here. If you factor out n minus 1 factorial, you'll be left with n minus k plus k, therefore giving you n minus 1 factorial times n, which is just n factorial. Right, and so this proves Pascal's formula using simply algebra. Right? We just manipulated the right-hand side and showed that it's equal to the left. Well, what's another way of proving it? Well, n minus k, remember, the binomial coefficient is the number of ways to choose k objects from a set of n, right? And where order doesn't matter. So we're just picking a subset of k objects from a set of n. And so we can do this in the following manner instead. Case 1. Given our set of n objects, 1, 2, 3, 4, and so on until n, what if we assume that the element 1 is picked for our subset, for the subset? Okay, well, if 1 is picked, what does that mean for us? This means we need to pick k minus 1 more objects from the rest of this set, from 2 to n, right? To fill out the rest of the subset that we're forming. So when 1 is picked, in case 1, this tells us, well, there are n minus 1, choose k minus 1, such subsets that contain the number 1. Case 2, on the other hand, well, now if we assume that the number 1 is not picked, well, that means we still need k objects, but now we're only picking, again, from the set from 2 to n, which has n minus 1 elements. Therefore, there are n minus 1 choose k such subsets that don't contain the number 1. And, well, what does the sum rule tell us? The sum rule says that the number of subsets of K or of size K taken from a set of N, right? So the total number of such subsets is equal to simply the sum of what we got from these two cases, right? Because this forms a partition of all the subsets, right? Either one is picked or one is not picked. And that's true for any subset of size K that we form. So this is by the sum rule. And therefore, this is equal to, well, just the number of K subsets from a set of size N, which is N choose K. Right, so what we just did here was to prove Pascal's formula using a different method than algebra, right? What we did was to count the same collection of things, right? The number of subsets, right? The number of K subsets of the set from 1 to N. And we counted it in two ways. The first way is just by directly using the binomial coefficient, right? Because that's what it's defined as. That's exactly it. And the second way is to break it up into cases and say, well, using the sum rule, I can also express it in this way on the right. So this is what is called a combinatorial argument, where you prove an identity or a formula or a theorem, right, by looking at the same object or the same collection of things and counting it in two different ways. And so the numbers or the quantities that you get from doing this counting in the first way and the second way, that should be an identity, right? Because you're just counting the same thing, right? So by counting the same set in two different ways, one shows that the two quantities obtained must be equal. And so let's look at another example. This is called the Chairperson Identity. This is the identity that says that K multiplied by the binomial coefficient N choose K is equal to N times N minus 1 choose K minus 1. And, well, as you'd expect, we can definitely do this using algebra, right? The left-hand side is K times N factorial over K factorial times N minus K factorial. And, well, the K cancels with the K down here, leaving us with N minus 1 factorial N minus K factorial. And let's take out a factor of N from the numerator, leaving us with N minus 1 factorial. Oops, this should be K minus 1 factorial. So N minus 1 factorial, K minus 1 factorial, N minus K factorial. And this is exactly the binomial coefficient N minus 1 choose K minus 1. Right? So it's quite easy to prove using algebra. Now let's try proving it using a combinatorial argument that will show us why this is called the Chairperson Identity. Okay, so imagine this. Suppose that you had N people. Let's just call them 1 to N. And you want to do the following. We would like to form a committee of K people picking from these N and elect a chair for the committee, right? Or a head or a leader for the committee. Right? So the question now is, how many ways are there to do this? Or is this the correct object that we need to count in two ways in order to get this identity? So let's look at this in one way first. Let's use the product rule, right? You can think of this as a two-step operation where in step 1, first you just form the committee. So how many ways are there? Well, you have n people, and you're picking k from them where the order doesn't matter, right? You're just forming a team of k out of n. Okay, well, now that you have your committee, now you pick a chair among these k people. How many ways are there to do so? Well, you already have k people in the committee, and you have to pick one of them, right? So it's k choose 1 or simply k. Therefore, by the product rule, there are k times n choose k such committee chair combinations. Right, so there are k times n choose k choices for the committee and the chair. So I won't use combinations here, I'll say maybe selections, right? Because combinations means something for us. Okay, so that's nice, right? We've found an object, which is these committee chair selections, such that counting those objects gives us exactly k times n choose k. But now let's try to count this a different way. What if we selected the chair first? Right, so how does that work? Well, okay, you have n people that you're starting with. So what if you just wanted to choose who the leader was first before you form the team? Well, so there are n ways to do so, right? It's n choose 1. From n people, you're picking one person. And now that you've picked a chair, how many ways are there to fill out the rest of the team? Right, so we want to fill out the rest of the committee. Well, we have how many spots left to fill? We need to pick k minus 1 more members, right? Because we already have 1, which is the chair. So k minus 1 more members from n minus 1 choices, right? Again, you already have a chair, so now you have only n minus 1 people to pick from. And there are n minus 1 choose k minus 1 ways. Therefore, again, by the product rule, there are n times n minus 1 choose k minus 1 ways, again, to form these committees and pick a chair. And this is a combinatorial argument now that shows us that k times n choose k and n times n minus 1 choose k minus 1 are simply two different ways of counting the same thing.